Hello, welcome to this conversation about exponential functions and equations. So in this video, we're going to talk about how do we graph specific exponential functions that have transformations which have been applied. Okay, so here is an example of an exponential function. And we want to be able to fill in a table of values. We want to look at this function and try to predict by our knowledge of transformations what's happened to our parent function. We want to plot points, sketch the curve, and then analyze the resulting graph. Okay, so we got a little bit of work to do, but we got this. All right, so if I'm looking at this function, and I have this -1 up here in the function part where the x is, what does that mean that the graph is doing? Okay, so this looks like we are shifting the graph 1 unit to the right. And we will kind of look at that when we're finished and see if that's actually true. All right, so let's go ahead and fill in the table. And I want you to remember that when I fill in the table, each of these x values are part of the exponent, and we want to subtract 1 from each of them before we apply the exponent. So 2 to the -2 minus 1, which is 2 to the -3rd, is 1 over 2 to the 3rd, or 1/8. 2 to the -1 minus 1 is 2 to the -2nd power, or 1 over 2 squared, which is 1/4. 2 to the 0 minus 1 is 2 to the -1 power, which is 1 over 2 to the 1st, which is 1/2. 2 to the 1 minus 1 is 2 to the 0, which is 1. And 2 to the 2 minus 1 is 2 to the 1st power, which is 2. So I've got a nice table of values. I can go ahead and plot these points on the axis. And when I plot them, I can kind of see that curve starting to emerge, right? All right, so then we're going to go ahead and sketch the curve by connecting the dots and using what we know about exponential functions to kind of extend that curve going infinitely up, and then have that curve flatten out to the left. All right, so now what we want to do is use this graph and analyze, okay? And remember we said that we thought that this was a transformation of our parent function that had been shifted 1 unit to the right. And if you were able to visualize the y-axis right here instead, you would see that that's exactly what had happened. We just took this entire graph and shifted it 1 unit to the right from our parent function. There's a lot of different things that we can ask for when we're analyzing the graphs of functions, but these particular items are pretty standard. So if I'm looking at this function, what's the domain? All right, and so the domain here is going to be -infinity to +infinity. That does not change at all. How about the range? This still looks like it is flattening out at a y value of 0. So we would say that the range is from 0 to infinity. Horizontal asymptote, that hasn't changed either. And you can see that I've already sketched that. It's kind of hard to see, but it's a purple dashed line, and that is y equals 0. X-intercept, this graph does not touch or cross the x-axis. And the y-intercept, that's going to be 1/2. You can see that on the y-axis, this red graph intersects at 1/2. You can also see that in our table. So our y-intercept is 1/2. Does this graph have a relative max or a relative min? And remember that a relative max is where this graph changes from increasing to decreasing. And so in this case, there is no relative max or min. All right, so what is the interval of increase then? Where is this graph actually increasing? And we can say the entire thing, right? So we are thinking about what is the domain of the entire graph. and that would be negative infinity to positive infinity. Now, the interval of decrease would be, where is this graph decreasing? And this is nowhere. It's not decreasing anywhere. Where is f of x greater than 0? For this, we are interested in where is the graph above the x-axis. And for this particular graph, it's everywhere, right? This graph does not dip below the x-axis at all. So where f of x is greater than 0 is negative infinity to positive infinity. And that does mean that where is a function less than 0? Where is it below the x-axis? And that's nowhere. So we would say NA here. Okay, let's try another example. For this example, we are looking at the function negative 2 raised to the x. And so what do you think has happened to our parent function here? This looks like it's been reflected over the x-axis. All right, so now let's fill in our table of values. And I want you to remember that we must follow the rules of order of operations, which means we must apply an exponent first and then negate the entire thing. So if I substitute this negative 2 in, I'm really saying 2 to the negative 2 power, which is 1/4, and then making it negative. So we would have negative 1/4 there. How about the next x value, which is 2 to the negative 1, which is 1/2, and then negate it, so we would have negative 1/2. 2 to the 0, we know that to be 1, negate it, we would have negative 1. 2 to the first is 2, make it negative, and we have negative 2. And 2 squared is 4. When we make it negative, it's negative 4. When we plot our points, we have that exponential curve beginning to emerge, but you can see that it does look like we have reflected it over the x-axis. Our parent function looked like this. Remember, it was traveling along the x-axis and then it shot up to the right. Here we're traveling along the x-axis and we're shooting down to the right. And when we sketch that curve, that's exactly what it looks like. So let's analyze this graph. Our domain will be exactly the same. From left to right, we're going negative infinity to positive infinity. Our range will be a little bit different though. Remember that range is low to high, and this, when we think about the lowest value on the y-axis or the least value on the y-axis that this graph encompasses, it's really negative infinity, right? But then it's coming all the way up, but it does not pass 0. So we'll say negative infinity to 0 here. Our horizontal asymptote is the same. That has not changed. Like we've had happen in the past, our x-intercept will not exist. So there is no x-intercept. Our y-intercept we can see is negative 1. We can see that from either the table or the graph. Is there a relative max or min here? Does this graph change from increasing to decreasing anywhere? And the answer to that is no. This graph is always decreasing, so there's no relative max or min. And we kind of just answered the next question, really. What is the interval of increase? Where is this graph increasing? And it's not, but it is decreasing everywhere it's defined. So we can say the interval of decrease is negative infinity to positive infinity. Now, where is this function greater than 0? Look at that graph and tell me, where is it above the x-axis? And you should be able to say it's not ever. It's NA here. And where is it below the x-axis? That would be everywhere it's defined, so negative infinity to positive infinity. All right, next example, we have y is equal to 2 raised to the x, and then take that quantity and subtract 1. All right, so what do we think is happening here? What do you think that negative 1 is doing? We had a negative 1 before, but it was up here with the x. Here, it's outside the exponent. So what do you think is happening? this does look like it should be shifted down 1 unit from our original parent function of y equals 2 to the x. Let's see. Let's go ahead and remember that we've got to apply the exponent first to the 2 and then subtract 1. So 2 to the negative 2. 2 to the negative 2 is 1 over 2 squared, which is 1/4, minus 1 is negative 3/4. 2 to the negative 1 is 1 over 2 to the first, is 1/2 minus 1, which is negative 1/2. 2 to the 0 is 1. 1 minus 1 is 0. 2 to the first is 2, minus 1 is 1, and 2 squared is 4, minus 1 is 3. Great table of values. Go ahead and plot those points and sketch the curve. Okay, so this does look like we have shifted that entire parent function down 1 unit, and you can see that I sketched my asymptote also to be down 1 unit. And in fact, if you have an exponential function in this form, this value will always be the horizontal asymptote. So that's a nice little thing to know. All right, so let's analyze this thing. Domain still negative infinity to positive infinity, but the range is different. Because this has been shifted down 1 unit, our range is going to extend from negative 1 all the way up to infinity, from that asymptote up. Our horizontal asymptote we already decided was y is equal to negative 1. Here we do have an x-intercept though. Look on the x-axis and see where this graph intersects it. Here we know the x-intercept to be 0. And the y-intercept is also 0, looking at just the y-axis. Is there a relative max or min here? No, we don't have one of those. What is the interval of increase though? Remember, where is this graph increasing? That is everywhere it's defined, which is negative infinity to positive infinity. And the interval of decrease, there is none. Now this one is a little trickier because we actually do have some of the graph above and below the x-axis. So when I'm thinking about this piece here, where is f of x greater than 0? I'm really thinking about, I shaded everything above the x-axis. What is the domain of the function in that shaded region? And so you're just thinking about from 0 to infinity, right? All those x values will be in that shaded region. So that is going to be where our function is greater than 0. Now how about where it's less than 0? Okay, so that's going to be everything below the x-axis. And that's going to be the other side of the graph, right? So everything to the left of 0 will be below the x-axis. And so we can say that's going to be from negative infinity all the way to 0. All right, that wraps it up for this video. And in the next video, we're going to talk about how to use the compound interest formulas. See you then.